Having seen the preparation and certain physical properties of benzene diazonium chlorides, it is now time to study various chemical reactions that happen in this case. Chemical reactions are an important aspect in the study of this benzene diazonium chloride salts, because these reactions actually help us to get various aromatic organic products very easily. This very easy sense is because of one particular factor that we happen to come across, that benzene is electron rich. So, suppose if you want to add a chlorine which is also electron negative, indicates that is also electron rich, benzene is also electron rich. So, two rich species cannot come and attach. So, therefore, this methodology makes it much easier for reactions. So, let us start the study of these reactions with the first set of reactions, which is nothing but a named reaction called as Sand-Meyer reaction. So, what is this Sand-Meyer reaction now? The Sand-Meyer reaction actually uses benzene diazonium halides as the starting reagent. It uses copper chloride, copper bromide, copper cyanide as its general reagents which are acting as catalysts, and HCl, HBr, KCN will act as the corresponding solvents. So, you are able to see that the combination of the catalyst and solvent depends on what is the molecule that you want to add to benzene ring. For example, if I am taking benzene ring along with this N2 plus and X minus, where X minus can generally be the chloride or the bromide salt, and if I want to add chlorine group into the direct substitution of benzene ring. Now, this is the catalyst which is there, and generally we know that catalyst we tend to write it on the arrow mark, and this happens in the presence of a solvent like HCl. So, what happens here is this is a highly unstable component, and therefore, the kind of product that we get here happens to be chlorobenzene, where remember that it is this Cl which has come and attacked the compound. N2 comes out as nitrogen gas, and this is the byproduct HX. Where did you get that HX? Is hydrogen from hydrochloric acid, X from this system. So, this is one type of a Sand-Meyer reaction. Supposing you want HBr with the above system, the catalyst that you are going to use is CuBr. This will give you the formation of bromobenzene, and the byproducts happen to be the same N2 and HX, because they are the ones which are basically going out from here, N2 and HX. Suppose you need a cyanobenzene, HCN, and then the catalyst that we use here is CuCN, where the final product that we tend to get is Cn plus N2 plus HX. So, what we basically understand is that from this set of reactions, a benzene diazonium chloride, when reacted with the corresponding solvent and a catalyst, will give us chlorobenzene, bromobenzene and cyanobenzene. Now, the question comes, why not fluorobenzene and iodobenzene? The reasons happen to be the same as we happen to discuss the reactivity of these compounds, that fluorobenzene is very reactive. So, taking HF, the reaction could be very volatile. And suppose if you go for iodobenzene, iodine is a very less reactive compound. So, going with HI also, the reaction may not proceed further. So, what Sand-Meyer reaction deals is the production of chlorobenzene, bromobenzene and cyanobenzene. So, you can just be aware of the catalysts that are being used in these cases. So, all these reactions come under the category of Sand-Meyer reaction. He happened to study these reactions in detail, and there was another scientist who happened to study the same set of reactants, and he found out the same set of products. The only difference that he employed was that instead of taking a copper chloride or a copper bromide, he took copper metal as a catalyst. So, what he did there was the same benzene diazonium chloride, where as an example we can see that benzene ring N2 plus and X minus, this compound he happened to react with HCl, which is exactly the same like Sand-Meyer reaction, but he did not use copper chloride, he just used copper metal, and we know very well that the role of the catalyst is just to see to it that the reaction proceeds in the faster way, it happens in a suitable way. So, therefore, Cl, where this Cl has been obtained from HCl, and the byproducts also happen to be the same, which is N2 and HX. So, the only difference that you are seeing between a Sand-Meyer reaction and a Gatterman reaction is that in Sand-Meyer it was a copper salt, copper chloride, copper bromide, where copper was in +1 state, whereas here this is copper metal is being utilized. Please do not confuse this reaction with the Gatterman-Koch reaction that you happen to study in the preparation of benzaldehyde. This is only Gatterman reaction because he was the scientist who happened to work with this reaction. So, having seen these two reactions now, which were basically the formations of corresponding chlorides and bromides, the question still lingers as to what about the preparation of iodides and fluorides. So, for the preparation of iodides, we could not use the earlier method because we know very well that these transition elements, and especially copper, is a highly unreactive metal. Copper is so very unreactive that most metals actually displace hydrogen atom, but copper cannot even react with hydrogen, and therefore, you are able to see that a stronger reagent is being used here, which is Ki, potassium iodide. Iodine is not easily introduced into the benzene ring directly because of its low reactivity, but presence of a strong reagent like Ki, it sees to it that the weaker iodine molecule which is there is able to attack the benzene ring, where you are able to get benzene along with iodine, which I can call it as iodobenzene, and the byproducts happen to be almost similar, where nitrogen gas is released and the ion here, which was a sort of a counter ion, that is K plus, will combine with Cl minus, and that is how KCl can be formed. Now, the question here is the X which is there, it can be either say chlorine or bromine, and depending on that the corresponding byproduct is formed. This reaction is important because iodine will not be possible to be introduced into a benzene ring directly because of its low reactivity. So, if this was about the introduction of an halogen with lower reactivity, the question of addition of fluorine is corresponding to the concept of high reactivity seen in fluoride molecules. Fluorine is pretty much reactive, and therefore, we tend to react this benzene diazonium chloride with fluoroboric acid, which is nothing but a combination of fluorine atom and boric acid, which is a combination of boron and hydrogen. So, what does this fluoroboric acid tend to do here is that it attacks the benzene diazonium chloride, forming arene diazonium fluoroborate, which on a strong heating can directly give us the fluoride arenes in these cases. The byproduct, you can see that there is still nitrogen atom being present in that case, where BF3 has been obtained as one of the byproducts, whereas fluorobenzene is the main product that we tend to see in this reaction. Please realize that fluoroboric acid is used and not HF, because HF is a highly reactive compound. Fluoroboric acid can be utilized for a controlled reaction in these cases. Similar to all these reactions where there was introduction of chloro group, bromo group, iodo group, cyano group, fluoro group, basically to say all the halogens and cyano group, we can also introduce hydrogen atom to the place where the nitrogen gas and the Cl minus can be released in these cases. So, what are the important aspects here is that this system can be analyzed where hypophosphorus acid, which is H3PO2, phosphorus acid is H3PO3, phosphoric acid is H3PO4, hypophosphorus acid is H3PO2. So, what we understand here in these cases is that the benzene diazonium chloride, if I take it N2 plus Cl minus, this when it is treated with H3PO2, which is hypophosphorus acid, and then with water, we are able to see that this hypophosphorus acid is acting like a reducing agent. And what is a reducing agent? It has two roles. One is either supply hydrogen or help in removal of oxygen. Now, there is no oxygen as such available in this case, but what it can do is, once you remove this part, which is N2 plus Cl minus, this becomes vacant and you can actually add hydrogen. Please remember here that the hydrogen atoms were there at this 5 positions and this position did not have hydrogen atom, whereas here the hydrogen atom is being introduced. So, where did this hydrogen atom come now? Basically is, this is the main product. The byproducts that are formed are, one is the nitrogen gas from here, then this H3PO2 will actually become H3PO3, and so one of the oxygen has come here, one hydrogen has come here, the other hydrogen will pick away the hydrochloric acid, which is the Cl minus has been formed there. So, what has happened in this case is, a hydrogen has been introduced here, which can be called like a reduction reaction. So, this is one of the methods for easy preparation of benzene ring. This method you hadn't studied in the first year, where you actually studied about hydrocarbons, because this compound was not introduced to you. But say from a competitive exam point of view, this can also be one of the methods for preparation of benzene. So, like utilization of hypophosphorus acid, we have another method where we can use alcohols like ethanol, which can form the benzene compounds along with various byproducts like nitrogen gas, ethanol, which is an aldehyde, as well as hydrochloric acid. The problem that we cannot use this reaction for aldehyde preparation because it is coming in as a mixture. So, we do not use it for aldehyde preparation as such, but definitely in the presence of benzene ring we can use it where benzene diazonium chloride compound is present. This has to be treated with an alcohol like ethanol. This is ethanol, we know it very well. This reaction, when I undertake, benzene ring is being present here. What has happened here now is, hydrogen has been introduced to this system, a byproduct nitrogen gas has come, CH3CHO, which is ethanol, and hydrochloric acid has been formed. So, what you understand by this system is that basically two hydrogen atoms have been reduced from the alcohol to aldehyde, which indicates that it has supported in donating the hydrogen atoms, and that is why we can call it like a reducing agent, and this overall reaction we can call it a reduction, because hydrogen atom is being attacked to your main product. So, this is how from benzene diazonium chlorides you can prepare the corresponding benzene rings, and this can be one of the very good methods, because generally what happens when we prepare benzene ring, it is an aromatic compound. Here, because the starting material is also aromatic in nature, conversion becomes pretty much easy. So, this is about the reduction of benzene diazonium chlorides and corresponding alcoholic compound of benzene, which we call it as a different class of compound, which is phenols, can also be formed. This reaction you also happen to see it in the aliphatic benzene diazonium chlorides which are formed, but that reaction happens because they are unstable in nature. So, we already know that these benzene diazonium chlorides, if you remember its preparation, we had actually used the temperature which was around 273 to 278 Kelvin only. This is the preparatory part. So, what I can tell here is that only at this temperature this reaction happens, or it becomes charred, it becomes black. Now, to this reaction, if I increase the temperature to say around 283, and naturally water molecules will be present because it is a solution, it directly reacts with water, and therefore benzene ring will combine with OH, which is a phenol. Where did you get the OH from? You got it from water, H plus OH minus. That is how the splitting happens, but here it is not the OH minus splitting which is important, it is the direct attack of the OH group, because this is an unstable system. So, what are the byproducts here? Naturally nitrogen gas has to come out, N2, and another hydrogen that was left over here will combine with Cl minus to form HCl. Please remember that attack of OH minus is difficult to benzene ring, because benzene ring is electron rich, OH minus is also nucleophile, but a presence of benzene diazonium chloride will make it like an substitution reaction where this entire part is removed and then OH minus has been substituted. So, this is one of the methods that we can employ to prepare phenols from benzene diazonium chlorides. Moving ahead now, formation of nitrobenzene. This formation is almost similar to the methodology that was employed in the preparation of fluorobenzenes earlier. So, for the fluorobenzenes, if you remember, you happen to use the HBF4 fluoroboric acid compound to get an intermediate, and because the intermediate is not very stable as such, we see that the NO2 group which has been present here can act directly to the benzene ring and thereby giving corresponding byproducts like nitrogen gas and NaBF4. Copper metal there will act like a catalyst. Why copper comes into play here once again is because NO2 is not reactive like fluorine or say highly unreactive like iodine. It is almost similar reactivity with say chlorine, bromine or cyanide groups. But the problem is the introduction of NO2 group cannot be made directly to the benzene diazonium chloride. It has been converted into the fluoroboro compound and then this reaction has been undertaken. So, this is the preparation of nitrobenzene, and now we see a couple of reactions which are actually utilized in dye formations. Now, what is a dye? Dye is actually a coloring matter which can actually be used on wool. We can use it in coloration of textiles, and this is the type of compounds that we use there. So, why this coloration is being given by these diazonium salts is because we know very well that color of the compound happens whenever electrons get excited to higher energy state, and while returning back they tend to give out their excess energy. So, that excess energy system is being utilized to form the corresponding dye which is stable in nature. So, let us see one of the dye preparations which has been present, where this benzene diazonium chloride, I am just writing it a little tilted form for my easy undertaking of this reaction, where this is the starting product, and to this when I write phenol. So, this is phenol OH, and actually hydrogen is there at all the positions H. It is just that I have just shown one position because that is the one main part which I need in this reaction. So, what happens here is that hydrogen and chlorine come out as byproduct, which is nothing but HCl. So, the moment hydrogen and chlorine come out as the byproducts, what happens to the main product is, this is the benzene ring which is present intact. To this benzene ring we had a nitrogen, and there was another nitrogen which is present, but this was a triple bonded compound. Now, what happens is, this triple bonded compound, one of the bond would like to go and attach with the benzene ring because a new type of conjugation compound is been formed. What is conjugation? That let us see later. Now, here what happens is, out of the 3 bonds, one bond is been broken up. So, what does that one bond do is, this one bond actually goes and combines with the benzene ring of phenol. So, what has happened here is HCl has come out as a byproduct, and here the one of the bonds has gone in combination with the benzene ring. Now, this lone pair has remained as usual intact, but what about this nitrogen now? This nitrogen is perfectly being stabilized and therefore, the lone pair retains on this. Now, what is conjugation is presence of double bond at alternative positions. That is what we call it as conjugation, and maybe at a higher class you will realize that those compounds which have a long conjugation chain, they show color, especially in the UV region, infrared region. I hope you must have come across these parts in tits and bits, but those are the regions which are away from our visible region. So, in the UV region you definitely see coloration of these compounds, and how can I call this as a conjugation compound is, I have a double bond here. So, in this case when I have to show the various points that are there, this is a double bond, there is no double bond here, then there is a double bond, no double bond, then again there is a double bond. Here there is again no double bond, though in benzene ring we know that the double bond keeps flickering, but there is a single bond and then a double bond is present, then again there is a gap, and you see that double bonds are present alternate in the benzene ring also. So what I basically would like to present here is that a large conjugation where alternate double bonding structures are present, those type of compounds give very good intense color, and that is what is actually utilized in the formation of dyes. So that physical property gives you very good dye formations for our day-to-day utility. So this was one dye formation where we used benzene diazonium chloride and phenol. Remember, phenol is acidic, but can these benzene diazonium chlorides react with bases? Now the same phenol, when I take an example of base where the OH which is there, let me replace it by NH2. Exactly the same reaction. All I have done now is the base, but it does not matter in this case whether that is an acid or a base, because reaction is not happening on NH2 or OH. Reaction is actually happening on the opposite side of that. And whether you take aniline or phenol, this hydrogen remains hydrogen itself, and then the byproduct is same. Only thing is the final product becomes different, where OH is being replaced by NH2. So this is how various types of dyes can be formed. We can see that the phenolic dye which was formed was an orange dye, whereas the aniline dye which was formed was yellow dye. That coloration depends on the light that is being radiated by the compounds, where electrons go to higher energy level and while coming back give back the energy in the form of corresponding colors. Having seen these parts, now the other factor you have to understand here is the naming that has been there, where the first compound is named as para-hydroxy azobenzene. Azo indicates nitrogen. It is not named as diazo because though two nitrogens are there, here it is basically a combination of two compounds which actually has one nitrogen and a benzene ring. Therefore, it is named as para-hydroxyazobenzene, para-amino azobenzene. So these are the two compounds that we come across. We call this as a coupling reaction. Coupling indicates couple, two. Two people have been mixed together, and that is how we call this. We do not call this as an addition reaction because I am sure you are able to see some byproducts. The reactions shown here have introduced base as the general catalysis solvent. So if the catalysis solvent is there, then maybe water can be formed as a byproduct in those cases, or you can directly get HCl as the byproduct. So this is all about the study of amines and benzene diazonium chlorides. We have a small assignment based on various aspects of benzene diazonium chlorides. The first one, how is benzene diazonium halide prepared? How is this halide compound prepared? The simple preparation reaction you can put up. Explain Gatterman reaction. I hope you remember that copper metal was used for this, and this reaction deals with introduction of chloro or bromo group for the benzene ring. How are phenols prepared from benzene diazonium chloride? So phenol reaction from benzene diazonium chloride is a pretty simple one, where water molecule is being directly put up on the benzene diazonium chloride and corresponding phenols are being obtained. So this completes the study of amines. In fact, if you see the order of study that we have, it completes the entire study of organic chemistry. Hope you have had a good time dealing with all these reactions, various physical properties, various chemical properties of these compounds, and wish you a good luck in understanding these concepts. Thank you. Sai Ram.